So as you know, we went out and bought this new laser. It's a 20 watt diode laser, and it cost us 145 quid from, what was it, Banggood I think, something like that. Anyway, we went out and paid for it. We did that because we wanted a replacement for the CO2 laser. Now, it was Richard Kerner, who came up with this, I think. I think it was him, but he was certainly mucking around with lots of lasers. Where he took a piece of this stuff, which is capped on tape, whacked it with the laser and turned it into a graphene supercapacitor. I always thought that was super cool. So I stuck it in the CO2 laser and totally failed to do it. There just wasn't enough oomph in that laser, I thought. But anyway, I mucked around with it for a couple of weeks, couldn't get it to work and gave up on it. But of course I wanted to revisit it with this new diode laser. So all I've done is taken a strip of this stuff and stick it onto a slide. So that's what's on there. And then I've drawn an interdigitated capacitor, and I'll show a picture of that. It looks like this. And I've put that into the program here, stuck the slide with the cap on underneath the laser, and there it is burning away. Okay, that's what came out of the laser. Actually, I think that's really quite impressive. It's got a real graphitic look to it, whereas before all it was doing was giving me kind of like a dirty black. But that actually has formed a graphene. It's a spongy graphene because we've got an explosion in there, but you can see it looks really graphitic. And now we need to test that as a supercapacitor. But that laser has done an awesome job. Okay, so I've got it on this capacitance meter, which is a Rigol DM3058. It's a pretty decent meter. All I've done is connect a couple of aluminium strips onto it so it can make good contact. And all by itself, without electrolyte, it's around about a nanofarad, 1.078 nanofarads. Now, that doesn't sound like a lot, but when you consider what it is, actually, that's really quite impressive, because something that was physically this size but 2 plates of aluminium will be around about 35 picofarads, so it's a lot more, maybe about 100 times more or something like that. All ballpark figures, but really very much more than it would be just as a plate capacitor. And of course that's to do with the surface area of the graphene. Now I haven't added any electrolyte, and I'm going to put a bit of tissue paper on it and a little bit of electrolyte, and we're going to measure the capacitance of that. So we bang a bit of electrolyte on it and we get 6.5 microfarads. Now again, that might not sound a lot, I mean microfarads, but remember it's supposed to be picofarads. Without electrolyte it's in the sort of nanofarads. With the electrolyte we're getting microfarads for that tiny piece of material. Now obviously there's a fair bit of playing around to it, but that is really quite a cool result. Okay, so we decided to give that a go courtesy of that new laser. Now I just did that really simple interdigitated thing and got what I thought was really quite an encouraging result, but obviously there's a whole load of things here. I mean, this is as thick as a piece of tape. You could do a whole load of designs, you could do layered up thicknesses of them, just a ton of things. I actually thought it was quite interesting that no electrolyte gave us such an improvement, because of course if we don't have electrolyte, we're not restricted to the voltage of the electrolyte. We can go up to what the breakdown voltage of the Kapton is. So lots and lots of possibilities. Now, a couple of details. I ran this at full laser power, 100%, 20 watt diode laser, 450 nanometers I think, and the speed I ran it at was between 200 and 250 millimeters per minute, so pretty slow. I found if I ran it slower, it burnt everything away, and if I ran it quicker, it didn't graphitize it, it just got it some sod. Anyway, I thought I'd share that with you because I thought it was really, really interesting, with a ton of possibilities for actually printing our own capacitors. I hope you enjoyed the video, and thank you very much for watching.